1.1 Experimental probabilities. So a probability is the likelihood of an event occurring. Probability experiment, focus on the word experiment. It's a well-defined process consisting of a number of trials. So this is just the number of times you repeat the experiment, okay, where clear outcomes and results are observed. Outcomes are the possible results of an experiment, where one event is the set of outcomes from an experiment and the trials is one of the tests. So, example 1. A 6-sided die is rolled. The number on the up face is recorded. Okay, when we say 6-sided die, we're assuming that the possible outcomes, kind of skipping to here, is 1 to 6. Or we can write it with squiggly brackets, 1, 2, 3, 4, 5, 6. Okay, so if it doesn't actually say, then the assumption can be they're labeled 1 to 6. So A, what is the event of the experiment? Okay, the event is actually rolling a die and recording the number on the up face. Okay, and what are the possible outcomes of the up face? Well, we already said 1 to 6, or in other words, 1, 2, 3, 4, 5, 6. We're going to learn this as our set notation, where we list the different outcomes and we can put a comma between them. Okay, the probability of an event A is denoted P at A. So this is going to be capital P for probability. Okay, so when we're talking about experimental probability, it's a probability based on actual trials. Okay, it's equal to the number of times an outcome happens. Okay, so this is connected with this. So the number of times event A happens divided by the total number of trials. Okay, this is often in maybe university or other textbooks called statistical probability or empirical probability. For the scope of this course, I usually stick to experimental probability. Okay, an example of this in real life is the free throw percentage. So Kobe scores 92 out of 100 free throws. In other words, you might be thinking, oh, make versus miss, which would be 50-50, right? 1 out of 2, 1 out of 2. However, because this is experimental, it would depend on how skilled this basketball player is, and therefore 92%. Okay, so I already explained these. When is experimental probability used? When dealing with real-life situations where actual observations are available. Okay, an example, sports, it's based on skill. Weather, it's based on past weather patterns. Traffic flow, it's based on routes and congestion, or insurance risk, like maybe a model to predict a premium and coverage. Okay, some of the probabilities. So 2 main focuses of the first couple units are going to be counting and probability. And a lot of times these equations will extrapolate and they'll be the same for, again, counting or probability. So for the sum of probabilities, what this is for a probability experiment in which there are n outcomes. If you add up all the probabilities, they'll equal 1. Okay, that 1 represents 100%. Okay, and P1 is just the probability of the first event. P2 is the probability of the second event, and so on, all the way to Pn, however many, not events, but outcomes there are. Okay, so likewise, the sum of counting, when counting the number of outcomes of an experiment, the total of outcomes can be found by adding the outcomes of each disjoint set, and we're going to get into this. Okay, so the number of, so the sum equals the number of elements in the universal set. So the number of items in set A, the number of items in set B. If we keep adding these, because there's no overlap, that's what disjoint means, okay, it will be the number of items in the universal set. The universal set specifically has the notation usually with a capital S. Okay, so let's actually see a hands-on example for experimental probability. A student spins a spinner 24 times. Okay, these are the results. So the results are red, yellow, or blue. Okay, 12, 4, and 8, those add to 24. So this right here is called a Riemann sum, and that just means add them all up. Okay, so when we're talking about experimental probability as a fraction, the experimental probability of rolling a red is going to be 12 out of 24. The experimental probability of rolling a yellow is going to be that 4 out of 24. And blue is going to be that 8 over 24. Now, I don't reduce these because they already have a common denominator. So therefore, if we add up all the numerators, we're going to get 24 out of 24, which is going to give us our 100% probability. Okay, what about a decimal? 12 over 24, I get 0.5. Okay, 4 divided by 24, I get 0.16, and then 7, because the 6 repeats. 8 divided by 24, 0.33, and that 3 repeats. If we were to add these up, okay, we do get 0.997. This is going to be a rounding error. Maybe if I put one more here, it's going to equal 1. It's okay if this is off by 0.1%. Okay, and as a percent, what we want to do is to this 0.5, we're going to multiply it by 100. So we get 50%. This is going to be 16.7%. I'm going to go ahead and round that up to 17%. Then it's going to add to 1 and 33%. Okay, therefore we get our 100%. Okay, so we did A. We determined the experimental probability of the spinner landing on each color. And then we expressed our answers as a fraction, a decimal, and a percent. Then we determined the sum. Okay, the sums were all in this final row. Okay, the sum of the favorable outcomes and explain what this means. Okay, so and then we're going to determine the sum of the probabilities and explain what that means. So the favorable outcomes is the total rolls, spins on the spinner. And that's going to equal the 24. Whereas the probabilities equal either 1 or 100%. So all, which means all the probabilities add to 100%. Okay, if we're asking ourselves, what could this spinner look like? Okay, so if we think about this, we usually draw a spinner circle, okay? Half of this could be red, right? So 50%. And then a third of it could be yellow. And then 17% of it could be blue. So that is what, based on our experiment, that's theoretically what the spinner would look like. However, we can't be certain. So E asks, is there a possible fourth color? So here's the thing. We could have red for most of it. Then we could have yellow for a lot of it and blue. But we could also have something like, say, green. Okay? There could be a fourth color. This is an experiment, so we could have just simply not landed on the fourth color. So an experiment is not going to be exactly theoretical. So we could have not landed on it. Okay, we have to still consider that because it's an experiment, it's random. Okay, mutually exclusive cases. So these are different cases that do not overlap or like they don't happen at the same time. Okay, so simultaneously. On a Venn diagram, we would have two circles with no overlap in the middle. So these are completely disjoint, okay, which is another word for mutually exclusive. So An example of this is a number can't be odd and even at the same time. And a person can't have blonde and black hair at the same time. And a food can't be a fruit and a vegetable at the same time. Like, there's no way that those answers are ever going to overlap. Okay? So when we have different cases that do not overlap, what we can do is we can apply the rule of sum, or in other words, the additive principle. So again, our two themes, counting and probability. So the rule of thumb for counting is the number of ways that either of two mutually exclusive events, A or B, occurring. So the number of A or B is going to be the number of A plus the number of B. And it's just simply adding all of the number of outcomes. Whereas probability is the exact same, but it's just going to be the probability of A or B. So the probability of A, or, which is going to be the plus sign, probability of B. Okay, so here's an example of that. The table shows the number of pizza slices ordered during rush hour over several days. So if we actually take a look and we want to fill out this chart, 98 plus 48 plus 51, we get 197 total slices were sold. So A, determine the total number of slices sold per day. That's good. Determine the experimental probability that a customer will order each type of pizza slice. So pepperoni is going to be the 98 over 197. Hawaiian is going to be 48 over 197. And vegetarian is going to be 51 over 197. And this is going to equal all 197 over 197. And all that really means is that you've accounted for all of the pizza slices. Okay, now we can take this and we can determine the number. Okay, so be careful between number versus probability. Okay, determine the number of customers who order a pepperoni or Hawaiian. Okay, so I'm going to do, C is going to be the number of pep or Hawaiian. And the thing is, you can't get one slice that has both pepperoni and Hawaiian on it, and therefore these are going to be mutually exclusive. When you order a slice, it's going to be either or, it's not going to be both. So number of people who ordered pepperoni was 98, and the number of people who ordered Hawaiian is 48. So the total number of people who ordered pepperoni or Hawaiian is 146. Now, likewise for D, determine the probability of a customer ordering pepperoni or Hawaiian. So this is the same idea, but it's going to be probability of pepperoni or Hawaiian. So we're going to go the probability of pepperoni plus the probability of Hawaiian. Okay, so the numerator is going to be the same. It's going to be 98 and 48, but because it's probability, it's going to be over 197. So when we express the answer, instead of just having 146 pepperoni or Hawaiian slices, we're going to have the probability of 146 over 197. Okay, and based on the information above, what advice should the owner tell the head chef to prepare for the lunch rush? So I would say he should tell the chef, the owner should tell the chef to make two times the pepperoni, I'll put pep, than Hawaiian or vegetarian. Okay, last topic today, subjective probability. This is the probability estimate based on intuition or experience. Okay, we're not going to actually assign numbers to this. It's just going to be an educated guess based on impossible, which is going to be essentially 0% chance it's happening, certain, which is 100% chance something's going to happen, and then anywhere in between. So unlikely, even would be 50-50, okay, or likely. So we're going to estimate the probability of the following, and we're going to provide a brief rationale. So what's the probability that it snows in Hamilton in July? I'm going to say unlikely. I'm almost going to say impossible. Okay, you could do both. Okay, so neither are wrong as long as your rationale supports it. So I've never had it snow in Hamilton in July. Okay, it has never snowed in Hamilton in July in my life. Okay? B, the person that sits next to you in a Starbucks coffee shop is a female. Okay? So you can do like two different ones. So you can say even. So it's like 50-50 male or female. Or I would even say likely. I find like the clientele at Starbucks is mainly women. Okay, and then C, the next pair of shoes purchased by an adult is the same size as the last pair. I'm going to say likely. You could say certain or you could say likely. I'm going to say likely. There's different makes. So adults are fully grown. So their feet are not growing anymore. But there are different makes of shoes. Different makes of shoes fit differently. So probably within a size.